Now let us look at some case studies of two of the more popular I/O protocols. One is PCI Express and the other is USB. So PCI Express is an I/O protocol for motherboards. So motherboards need a bus to connect the I/O elements. For example, you can have a large motherboard like this with the CPU's chip over here, and you'll have a lot of I/O cards at different points. So they need to be connected to the CPU in some way, right? So we need a bus to connect all the I/O elements to the CPU. So there were many popular buses in the late 90s. Two of them in particular were popular. One was the PCI, the Peripheral Component Interconnect bus, and the AGP, the Accelerated Graphics Port bus. So nowadays, since most graphics processors have come on chip, have come inside the CPU's chip, right? AGP bus is kind of out of fashion. So after subsequent standardization, the PCI bus, and also, I need to slightly take back my statement, because there are also some other motherboards which can have a separate GPU, for high performance gaming systems, can have a separate GPU on the motherboard, where also this needs to be connected to the CPU. So since all of them will be connected using a bus, a standardization effort led to the PCI Express standard, and the previous bus technologies, PCI and AGP, were somewhat deprecated, and they are not as of now being used, at least in new systems. So the PCI Express standard, which you can find on their website, defines the concept of a PCI lane, which is a high-speed serial bus. So serial bus means it sends one bit at a time. So a lane per se does not use parallel links, mainly because it's a very, very high frequency bus, so the time between successive bits is very small. So there is a possibility of a variable amount of delay, different amounts of delay across the different links, if we have parallel lanes. So synchronization becomes difficult, but it's not impossible. But in general, inside a single PCI lane, we transmit a single bit at a time. But mind you, it is you can have a bus with parallel links as well. So there are trade-offs, and one trade-off is it needs to be slightly slower. So in general, in a PCI Express, so PCI Express is a very, very broad standard, and it is mainly meant for motherboard buses, right? Not for others. So buses on the motherboards are very high bandwidth. That is a usage, a peripheral component interconnect. It's an express bus. Express means fast. So on the PowerPoint presentation, if users click this link, they can go to the standard of the PCI Express bus. So let's take a look at the topology first. So this is basically a point-to-point bus with multiple lanes. And a lane, as we have defined, is a single bit full duplex channel with data striping. So I'll tell you in a second what this is. So furthermore, so let's say, there are two nodes. There is a GPU and there is a CPU. They talk to each other via a PCI Express bus. So it is possible to have, a single lane, or you can have multiple lanes as well. So in the multiple lanes, you can send multiple bits in parallel, which we basically mean by data striping. So of course, sending data across multiple lanes has the issue of synchronization, that at the receiver, we sort of have to synchronize the data. So that is difficult, but can be done. And the number of lanes can vary anywhere from 1 to 32. So now let's take a look at the different layers of the PCI-X bus using the same terminology that we have defined. So we have defined a physical layer. So physical layer has the signaling part. So signaling is LVDS based differential signaling. So every lane basically has two wires, and you monitor the difference between them. The encoding is novel. This is not something we have covered, but readers can definitely read about this on the web. So it's called 8-bit, 10-bit encoding. Many other buses also use this. So here what happens is that every 8-bit piece of data, every 8-bit frame is actually converted to a 10-bit frame, and the additional bits give us a little bit of error detection and correction capability. So this is called 8-bit to 10-bit encoding, which makes the signaling somewhat more robust to bit flips at least. And the timing is source synchronous in the sense that we send the clock along with the signal such that it can be recovered at the side of the receiver. Now let's come to the data link layer. So the frame size is 1 byte, right? So that's how much we send, but of course we use the 8-bit, 10-bit encoding. The error correction that we have is 32-bit CRC. So recall that CRC codes are very useful, especially when we have a burst of errors. The PCI Express bus can sustain split transactions. So this is a requirement of almost all high performance buses that deal with modern devices, that we don't want to lock up the bus, right, for one single transaction. And the bandwidth that we can support is 250 megabytes per second per lane. So this is it's not super fast, but it's not super slow either. And if you take a look at it, a DVD which is around 5 gigabytes, right, which stores an entire movie. So this roughly is 5000 megabytes. So to transfer the contents, to read the contents of the entire DVD and transfer it to another device which can accept data at this rate, it will take 5000 by 250 seconds, which is 20 seconds to read the contents of a DVD, or to read large parts of it. So in that sense, it is not extremely slow. It's a fairly high performance bus. But yes, we could have faster alternatives such as optical buses and so on. So we are not discussing them in this lecture, but readers can find the details of novel technologies with fairly higher bandwidths. And the network layer, so we have a set of routing nodes called switches, which allow us to route data between different point-to-point links. Now let's consider the USB bus, the Universal Serial Bus. So recall that the USB bus we have also discussed in the past, and what we discussed is that it's very popular. Any device nowadays that you want to connect to the computer basically is connected via a USB bus. Almost all laptops, desktops, phones have a USB connector. So it has become a de facto standard today for connecting all types of peripherals to a computer. So it's not a motherboard bus. So if let's say this is your laptop, right, and you want to connect an external device such as a mouse, so then this is connected via a USB port. So you can also connect scanners, printers, cell phones, pen drives, you name it. And so USB ports do allow pretty high speed signaling and traffic. Also there are three kinds of USB. So there is starting from slow USB to super fast USB. But in any case, for all our externally connected I/O devices, USB is a fairly popular and high performing technology. So it has up till now not proved to be a bottleneck for all our current devices. So each USB port or host can be connected to a set of devices arranged as a tree. So what you can do is that you can connect this USB port to what's called a hub. So the hub can have 4 ports which can connect to few more devices, and maybe this can also be a hub which can again connect to few more devices. You can have a tree of devices, right, connecting to a single USB port. So each of the internal nodes would be a hub, and we can connect a total of 127 devices including hubs, of course, to a max depth of 5 to a single USB port. Let us move forward. So let's look at a basic USB connector. So a lot of people would have seen USB connectors on the side of their desktop or front of their desktop, side of the laptops. So there's a normal USB connector which has 4 pins. So one of the pins, so recall that USB is both a data transfer and a power delivery bus, right? So I'll tell you why the latter is required. So the requirement for the latter is like this, that there might be many devices, like small mice or pen tablets or flash drives which we insert and they don't have a battery or any power of their own. That's the reason it is necessary for the USB drive to actually supply the power. And in this way, the device can run. In addition, there are some other benefits of this. For example, you can charge your phone with a laptop. That was not the original intent though. So that's the reason we have a VCC pin, which is a supply pin that provides 5 volt DC power, and we have a ground pin. In addition, we have 2 pins for data transfer, and since the data transfer happens via differential pair, similar to LVDS, we have 2 pins, data positive and data negative pin. So their mean voltage is 3.3 volts and the voltage swing is around 3.3 volts. So for micro and mini USB ports, so micro and mini USB ports you will typically find in smaller devices like phones and tablets. So they have a different connector. The standard USB connector does not go in there. So it is kind of large for these devices. They have a smaller, significantly smaller connector. And these devices actually have 5 pins. In fact, I'm at the moment I'm taking a look at my phone's micro USB port. So that has, I'm sorry, the mini USB port, and that has 5 pins. So the additional pin is called ID. The ID pin basically helps us differentiate between a device and a host, which means that let's say if I'm connecting my mouse to a computer, my mouse becomes the device and the computer becomes the host. So in some cases, it is necessary to break the symmetry. Especially when you have a tree of devices, you want data to either flow towards the host or towards the devices. So it gives it a sense of direction, that which way the communication is happening, and this is to differentiate between the device and the host. So we use the signaling mechanism that we have is the NRZI signaling mechanism with dummy bits, of course, for clock recovery. So recall that we needed dummy bits. The reason being that if you have a constant voltage, then you'll not be able to recover the clock. We might fall out of synchrony. So that is the reason it was necessary to force a 1 sometimes, such that at least there'll be some transitions and the clock can be recovered. So the USB data link layer actually defines 4 kind of packets. So we have control messages. So the control messages are used to configure devices, and so they are basically sent at the beginning of a USB connection to ensure that the device is configured properly and it can talk to the computer. We have interrupts. So for example, when we press a key on the keyboard, we have an interrupt. So the interrupt goes to the computer. We have bulk transfer, which has pretty huge frame sizes, and a large amount of data is transferred. So you can print a large page, right, with bulk transfer. So this is used mainly for printers and so on. And then you have isochronous data transfer, which means data transfer at a fixed rate where the rate is known in advance. For example, this can hold for a camera, right? Web camera or something, right? So you have these four kinds of data transfer modes: control, interrupt, bulk, and isochronous, depending upon the kind of device that is being used. So of course, these concepts span across multiple layers in the stack, but of course, they have the physical layer is the same for all. But starting from the data link layer, there is some amount of differentiation. And of course, like PCI Express and all modern buses, USB is also a split transaction bus, so it does not lock any channel per se. So the network layer of any USB device is decided like this, that every USB host, every single device that is connected is assigned a 7-bit ID by the host. So the total number of devices that you can connect is limited to 128, because this is 2 raised to the power 7, which is 128. So every USB device, furthermore, defines a set of I/O ports. So recall that a port is both a physical thing because it allows you to connect, also it's a logical abstraction. So every USB device typically has 16 in ports and 16 out ports. So basically, since each port, this is 2 raised to the power 4. So basically, a port has a unique 11-bit address, which is the 7-bit device ID, and the 4-bit port ID, which make it a unique 11-bit address. So software drivers talk to the device by sending messages to the corresponding port. Right, so this is sort of very similar to what we saw that happens on x86 systems and their motherboards, that every device defines a set of ports, and the software essentially sends messages to those ports and talks to the devices basically by reading and writing to those ports. Subsequently, we have the protocol layer. So in the protocol layer, we have different kinds of protocols, but by far the most popular and the most commonly implemented are what are called a stream pipe and a message pipe. So in a stream pipe, the structure is unstructured. So the structure of communication is unstructured, which basically means that we are just sending data, and it's not per se synchronous. And one such example would be some sort of a feed connecting a sensor or other kinds of devices where we are not really interested in the reliability of the transmission, or neither are we interested in some sort of a rate limiting. As compared to that, what is slightly more popular is the message pipe, which is a structured communication with a handshaking mechanism. So there is a way for the receiver to tell the sender that it has received the data. So we can think of stream pipes as basically a method where data simply comes in to the computer, right? Where data simply comes into the computer, and there is no communication, there is no defined format. And a lot of devices that use unidirectional communication, like some of the simple web cameras, would basically send a stream of data using the stream pipe mechanism. However, if we consider another device where it is connected via USB, and then there is a fair amount of control that is happening, in the sense that the computer is sending messages to the device and the device is sending messages back. So that can be maybe something like putting in a flash drive or something, where we are essentially initiating several transactions. So in that case, we would rather use something which is more structured, which is a message pipe. So the summary of USB is like this, that it can be used to connect many kinds of peripheral devices: keyboards, mice, web cameras, pen drives, almost anything. So nowadays, it has become the de facto standard to connect devices with USB links. And also, most of the modern phones are actually charged with USB links. So the connection is a point-to-point serial connection, right? So it's a universal serial bus after all. And maybe I've missed this part, but yes, the full form of USB is Universal Serial Bus. And why serial? Well, it's the same logic as PCI Express. We try to send, uh, we trying to send a single bit at a time instead of multiple bits because synchronizing across the bits is difficult. And also, since these are external connectors, the links are fairly long. So there is a fair amount of noise that these links are exposed to. As a result, transmitting more bits at a time terribly limits the bandwidth. So we have point-to-point links, which are again serial single-bit links, and it's a half-duplex communication. So in the sense that it's not possible for the sender and receiver to be talking at the same time. Let's look at the physical layer. So the signaling is LVDS-based signaling. So that's almost common for almost all high-performance I/O protocols. The encoding is NRZI, but however, a transition is represented by a logical 0, not by a logical 1. And the timing per se is asynchronous in the sense the clock is recovered from the NRZI transitions. But since we don't want, if we have a lot of ones, means that the voltage remains constant, so we might not be able to recover the clock. So we add a dummy 0 after 6 continuous ones for clock recovery. Right, so for clock recovery, this is done that we add a dummy 0 after 6 continuous ones. So this ensures that we are at least able to see some transitions such that the clock can be recovered at the other side, the side of the receiver. So the frame size varies from 46 bits to 1058 bits depending upon the type of communication. If it's a small interrupt, the frame size can be small, but if you are doing a bulk transfer, the frame size will be much larger. The error correction is CRC, so recall that PCI Express also use CRC. CRC is great when there are a burst of errors. Again, it's a split transaction bus. So there are three kinds of USB formats that have been defined, and they use, they use different frequencies. So there is a low speed USB which is only at 192 kilobytes per second. So this technology is fairly old, but nevertheless, this can be used for mice and keyboards and so on because they don't generate a lot of data anyway. 1.5 megabytes per second will be for web cameras and other devices which are at least generating some amount of video. So this is called full speed USB. And now we have a much faster 60 megabytes per second high speed USB, which is for HD quality devices. So there is a spectrum of USB protocols for these three devices, but the basic structure for all of them is the same. The network layer, the addressing is like this: that we have a 4-bit port. So ports are also called endpoints in USB. So every is assigned 16 input ports and 16 output ports. So they have a 4-bit ID. So 7 plus 4 it becomes an 11-bit ID. We use a tree of hubs. So where one hub can have one upstream port and up to 4 downstream ports. So upstream is essentially towards the host and downstream is towards other devices. And we can support a maximum of 127 devices per USB port on the computer. So if this is the computer, right, or the host, then for one port we can support maximum of a tree of 127 devices, inclusive of hubs. So the connections, well, we can have two pipes. You can have a message pipe, which is structured and acknowledged, and a stream pipe, which is unstructured. And we can have 4 types of traffic, which will have different frame sizes, and of course, even at the protocol layer. So as was discussed, for these 4 kinds of traffic, there are changes in all layers. So starting with a different frame size in the data link layer to better network support at the network layer to some more support at the protocol layer. So we have 4 kinds of protocols. The control is for control messages. Interrupt is for a keyboard and mouse interrupt, right? Where something is being sent to the processor for immediate action. Bulk will be mainly for printers, and isochronous is where the rate of data sending is constant. So that would be a web camera or other kinds of recording devices. So now that we have seen the case studies of two I/O protocols, namely PCI Express and USB, let us look at storage media, which is the last part of this chapter. So our hard disks, optical drives and solid state drives are the three kinds of storage media that I want to discuss. So what is storage media? Well, so if I turn off my computer, all the data inside the processor and in the memory devices like the DRAM and so on, all of them get erased. But still our files and our data and images and everything else stay, right? The reason they stay is that we have some permanent storage media, namely hard disks, optical drives, and solid state drives, our USB keys and so on, which maintain data even if the system is powered off. All right, so even if we turn off the system, our data still remains. So let's take a look at hard disks first. Then we'll take a look at optical drives, CDs, and DVDs. And at the end, we'll take a look at solid state drives. So hard disks store data basically via having small magnets, and extremely small magnets, a sequence of tiny magnets. So we use NRZI encoding. So let's see how. So a given magnet will have a north pole and a south pole. See, in this case, if you see, so whenever two magnets are aligned in the same direction, so if you consider this, right? So in this case, the magnetic field, let's assume that it flows from south to north. It is aligned in the same direction. So once a piece of metal actually flows over this, it will, of course, a moving magnet, a moving piece of metal on a magnetic field, a certain amount of EMF will be introduced. But also another thing is that if, this will be one kind of a signal. But if you look at this point, the magnetic field essentially here is reversing, right? So here we have one magnet which is north south and another one south north. So the magnetic field at the junction of these two small magnets, in a sense, is reversing. So if the head actually passes over this, it will have a much larger potential jump. The reason being that we are moving it through a changing magnetic field. So this is how we will infer at this point when there is a change in the magnetic field, a bigger change, that we are encoding a logical 1, and if there is a smaller change or no change, we are encoding a logical 0. Similarly here, the direction of the magnets is the same, direction of magnetic fields is the same. So here we basically assume that since the directions of both the magnets are the same, we assume that it's a logical 0. And here the direction again changes, right? So since the direction again changes, we assume it's a logical 1. So this is exactly the NRZI encoding, where we assume that for no transitions it's a 0. For a transition there is a logical 1. And to ensure that we don't fall out of sync, we also add dummy bits. So this we can see is NRZI encoding. It is not necessary that it will always be at the level of signals. It can be also at the level of the orientation of magnets, as we see here, that if the magnetic field is the same, we assume it's a logical 0. However, if the magnetic field is different, we assume that it's a logical 1, right? And this is an example of NRZI encoding, albeit with, in a different setting, but nevertheless it is NRZI. And this is exactly what is happening in our hard disks. But as you can see, a typical hard disk, which is not very large, it actually fits. It doesn't fit on a palm, but it's slightly larger than a palm. And hard disk is incredibly storage efficient. So one hard disk can easily store, as of today, 1 terabyte at that size. So 1 terabyte is 1024 gigabytes. So roughly it is 10 to the power 12 bytes. So these magnets are extremely small. So these magnets are very, 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 very small, and we have a lot of millions, billions of such magnets on a magnetic surface. So the way we read them is that we basically move a metallic head on the magnets. There's a relative motion between metal and the magnets, and we sense the magnetic field, whether there's a change in it or whether the magnetic field is remaining the same. So the architecture of a hard disk is somewhat like this, that it actually contains multiple such disks, but let's take a look at a single disk. So a single disk is called a platter, right? So a platter is basically a metallic disk with, of course, a hole in the middle. So you can, it's a donut shape. It looks like pretty much like a CD actually, with a hole in the middle, and it is divided into these concentric rings. So each such concentric ring, as you can see over here, is actually called a track, and each track basically contains these small, small magnets. Okay, so let me draw these magnets. So each of these magnets, if I consider this magnet and sort of blow it up, it has a south pole and a north pole, right? So each of these magnets has a certain orientation, and the bits are basically stored in the relative orientations of these magnets. So what is a track? Well, a track is a concentric ring, and what is a sector? Well, a sector is a portion of the track. All right, so it is basically one portion, as we can see, a certain angular portion of the track. So for example, this is a sector, this is one more sector, and so on. So what are the three terms that we have defined now? Well, we have defined a platter. A platter is basically a ring with a hole in the middle. The hole in the middle is for basically spinning this ring. Then we have defined the notion of a track, where a track is one of the concentric circles, which contains many, many magnets that are arranged side by side. And we have defined a sector, which basically means that a track is divided into fixed size sectors. So typically in a hard disk, the sector size is a constant. So one of the common values is it can be 512 bytes. So the sector size is typically constant, and a sector will basically be a portion of the track, right? So these are the three terms that we have defined: a platter, a track, and a sector. So the way that the hard disk works is somewhat like this, that we have multiple platters. If you look at it, if we count here, this is the first platter, second, third, and fourth. So we basically have four platters over here in the hard disk. So these four platters are connected together with a spindle. So basically the platters are rotating like this, right, at a fairly high speed. So the speed is typically 5400 RPM, or revolutions per minute. Which is 90 revolutions per second. All right. So this is it basically rotates very, very quickly. So the speed of rotation is extremely high. So the rotation is very, very quick. And what we do is also then what we have is that we have this head whose job is to read the bits that are there on the platter. So let me just remove the ink on the screen and let's focus on the head a little bit more. So the head is basically a piece of very, very sophisticated electronics. But at the core of the head, all that it has is that it has a little bit of metal over here, which essentially senses the EMF. It's a small metallic coil, where at the both ends of it a potential is induced because of the changing magnetic field, and this small potential is sensed by the electronics of the head, and depending upon the change in the magnetic field, we infer a logical 1 or a logical 0. So this is very, very sophisticated in the sense that the amount of voltage changes that we are looking at is actually very small. So that's the reason the head has to be very, very close to the surface of the disk. Furthermore, please note that the rotation of the head is actually angular, in the sense that the head is connected over here to a motor which can either rotate it in this direction or rotate it in that direction, which means that again the head can either rotate in this direction or rotate in that direction. So it is not sliding along the radius of the platter, rather it is it is basically sliding this way or sliding that way in a circular arc. And so this allows us to actually position the head on the right track, because recall that a platter actually has multiple tracks, and so we need to position the head on the right track. So this will be done by first rotating the head. Then we need to wait for the right sector which needs to rotate and come under the head. After that, we need to start reading the data, which basically means we need to sense the changes in the changes in the potential that is being induced because of the change in the magnetic field, and then read the data for the sector, process it, and send it to the processor. So the head is a very small device which is over here, and it is rotated with an arm. So of course, if we have multiple platters, we'll have multiple heads. I'm not showing multiple, but I'll show that in a separate diagram, where we'll not have one head, but we'll have multiple heads, one for each platter. So this is shown over here. So this particular diagram shows us a two platter system, where each platter has two recording surfaces, the top surface here and the bottom surface here, and again the top and the bottom. Both the platters are connected to a spindle, and the spindle is connected with a spindle motor, where at a fixed RPM, both the platters rotate. So recall that these disks are actually rotating at a very high speed. So something like 5400 RPM or 7200 RPM. So for each recording surface, we have one more spindle over here with the arms, and there is a read-write head at the bottom of each arm. So it can either read by sensing the changes in the magnetic field, or it can write by basically inducing a magnetic field such that the magnets orient themselves the way that we want them to be oriented in response to an external field. So basically for each recording surface we have one head. So this has one head at the top, one for the bottom, which is this arm. Again one head for the top surface and one more head for the bottom surface. So this will have four heads. So it is actually not possible for us to read data from multiple platters simultaneously. The reason being that coordinating all four heads is somewhat difficult. That's the reason we basically read from only one surface or one platter at a time. And all of these heads, which are all of these connected via arms to this spindle over here, this is connected to an actuator whose job is to rotate the heads a little bit anti-clockwise or a little bit clockwise, such that they align under the right track. So of course this head is in the diagram could have been slightly more accurate, in the sense the head actually should have been longer such that it reaches the innermost track, but hopefully the readers will give me that much of slack. So what I again mean is that the head should have been this arm should have been longer, so the head reaches here, and then of course the head could rotate in this direction or in that direction, such that it could reach all the tracks on the platter. But anyway, let's leave this much of inaccuracy in the drawing and let's go forward. So then what happens is that we have the electronics of the drive, which basically controls the spindle motor. And so recall that all the disks rotate at a fixed RPM. So you have constant angular velocity, and we then basically read data, and the data read data or we write data. And so via the drive electronics, it comes to the bus interface, where if the hard disk is connected by a PCI Express bus, then the data traverses by the bus to the CPU. So we can either read data from the hard disk or we can write data. But the greatness of a hard disk is that since data is stored in terms of sequences of magnets, we don't lose the magnetism once we turn off the computer, right? So this is a method of stable data storage even when the computer is turned off. So let us now look at the different aspects of reading data from a hard disk. The first is to rotate the head and put it on the correct track. So this part of the latency, where we essentially rotate the head and put the head on the right track. So maybe we need to rotate this and bring it to the end, or we maybe need to bring it over here. So this time is called the seek time. Once we are on the right track, we need to wait for the desired sector to come under the head, right? So this we need to do such that whatever sector. So recall that the track is divided into sectors. So we need to wait for the right sector to rotate and come under the head. This is called the rotational latency, where of course the assumption is that the hard disk rotates at constant angular velocity, which is true for most hard disks in the market. In almost 100% of the hard disks rotate with constant angular velocity. Subsequently, we read or write the data. So we need to perform error checking, we need to do any error correction if any errors have been induced, and we need to do the framing, which means take a set of bits and create a much larger frame out of it. And in the case of read, we need to transfer data back to the CPU, which is the transfer time. So if I include all of these components, where the transfer basically starts when the head is on the first bit of the sector, what we will see is the total disk access time is the seek time, which again you're getting the head on the right track. Once you're on the right track, the rotational latency gets the head to the right sector. Once the head is on the first bit of the sector, the time it takes to basically read out all the data, perform error checking, the framing, and transferring it to the CPU is called the transfer time. So the sum of these times is the time it requires to actually perform a hard disk access. What are the three components once again? Is the seek time, the rotational latency, and the transfer time. So let us now look at what is a logical block address and what's a physical block address. So software programs use the logical block address to address a hard disk block, which is also called a sector. So we'll use the term a hard disk block and a sector interchangeably. So because in the software parlance it's called a block, in the hard disk parlance it's called a sector, but they actually mean the same thing. So what happens is that the hard disk internally has an addressing scheme where for the different concurrent tracks that we have and for the different sectors, they have a unique physical address. So the hard disk will internally convert the logical address that the CPU or the program is sending to a physical address, and the physical address actually has the recording surface, which platter it is, which track and which sector. So most hard disks will essentially dedicate a recording surface for storing this information, which tells it given a certain logical address. So where of course, what is a logical address in simple terms? If let's say it's a 128 gigabyte hard disk, we can think of the hard disk as one large array of bytes from 0 till 128 gigabytes, right? 128 gigabytes minus 1. So of course this is divided into 512 byte sectors. So every sector will have an address. This has to be mapped to a physical address. So we have a recording surface which just has this mapping. In addition, you can have a small DRAM cache with the hard disk, which can store some of the most recently used mappings between logical blocks. So logical block sort of similar to virtual memory. We assume that every block has an address, even though it can be stored in different parts of the hard disk. So such kind of a logical to a physical block mapping can be stored on the hard disk, which it typically is. In addition, we can have a small subset of the mappings in a small DRAM device which is there inside the hard disk itself, such that the latency for finding out the mapping is somewhat reduced. What the hard disk can further do is, let's assume a sector gets damaged permanently, right? So because of some reasons, the magnets lose their magnetism. So in that case, what we can do is that we can use this recording surface, which we have dedicated it for saving information about the disk, to also have the data for all the bad sectors, at least record which sectors are bad. And once we have a bad sector, we can sort of remove its mapping and we can remap logical sectors to other healthy physical sectors. So let's assume that there was a logical block ID and it was mapped to a certain sector, right? Later on, we find that this sector has failed in the sense that the magnets that are there in the sector don't work anymore. So we can remove this mapping. We can instead map it to one more physical sector, which is fine. So all of these things are possible inside the hard disk because the actual track, sector, and recording surface information is not visible outside the hard disk. The only thing that is visible outside the hard disk is basically an abstraction. So the abstraction treats a hard disk as one huge large array of bytes. So now that we have discussed our hard disks, we are not done yet because a hard disk, as we have defined, is a fairly simple device. So the CPU basically sees a single hard drive as a large array of bytes, right? So the size of the hard drive is 1 terabyte. The CPU sees this as a 10 to the power 12 entry array of bytes. And of course, internally, it is implemented. It's a fairly complicated structure. In a sense, it can have one spindle and it can have many recording surfaces connected to it. And it will have a lot of platters and recording surfaces. They will have their own tracks and sectors. So, but all of this complexity is being hidden from the user, which in this case is the CPU, because it just perceives the hard disk as a very simple device. But recall that internally the hard disk is a fairly difficult device. It has magnets. If you, let's say, expose a hard disk to a strong electromagnetic field, it might lose its data. Also, one more negative aspect of hard disks, if we sort of go back to this figure, is that it has a lot of mechanical components. For example, this motor is a mechanical component. All of these spindles and these platters are mechanical components. The actuator here for the head arms are also mechanical components. Moreover, the head needs to be actually a little bit above the spindle. This little bit can be, several nanometers. So in a sense, the hard disk is very sensitive to damage. If you, let's say, drop a hard disk or let's say the temperature increases, the chances of failure of a hard disk actually become very high, mainly because it uses mechanical components. So of course we have nicely abstracted out a hard disk with this formula over here, which tells us that we first seek the right track, that's the seek time, then we seek the right small c over here, then we seek the right sector, then we transfer the data. But in reality, a hard disk can have failures because there are too many mechanical components and there is very high temperature sensitivity. So we looked at one way of fixing the problem of the low reliability of hard disks by basically having this, dedicating one recording surface to saving a mapping. For a mapping is between a logical block ID, which is a logical group of 512 bytes as perceived by the CPU, and a physical block ID, which is an actual sector within the hard disk. Just in case if this sector goes bad, we can always remap it to another sector. But what happens to the data? We'll end up losing the data, right? Which is not something that is desirable. Especially, imagine that a bank has a set of hard disks and one hard disk goes bad. It should not be the case that somebody's account details are just gone. So to sort of rectify all of these issues and make ourselves immune to disk failures, for which there are many reasons, mechanical reasons, temperature reasons, what do? We use what is called RAID, which means redundant array of inexpensive disks, which basically means don't have one hard disk but have multiple. That will allow you to tolerate faults and also recover from failures. In addition, a RAID system also increases the total bandwidth, which means that so what happens in a current system? In a current system, if you want to read two different blocks from the same disk, we need to read them serially, which means one after the other. This is low bandwidth. We can increase the bandwidth if we can read from multiple disks in parallel. So we'll see how to do it, which is by using RAID. So a RAID has twin advantages. One advantage of RAID is higher reliability, of course. So if you have it sort of makes you immune to failures. So higher reliability. Where a disk fails or a part of a disk fails, we can still recover. And the other is higher bandwidth. So let us consider the simplest RAID configuration, which is RAID 0. So in this case, what we do is that we consider two disks, right? We consider disk 1 and we consider disk 2. And let us consider each block to be 512 bytes. So we keep block B1 in disk 1, block B2 in disk 2. So essentially all the odd number blocks, we keep them on disk 1, and all the even numbered blocks, we keep them on disk 2. So distributing data in this manner across disks is is called as data striping. So in this case, of course, there is no additional reliability. However, it allows us to read even and odd blocks in parallel. For example, if let's say we're trying to print a page and the page is in blocks B3 and B4, we can then, since there are two disks, and we'll have one CPU which can send the data to the I/O ports, or we can even better, we might have DMA which will read the data from the hard disks and directly write it to memory from where it can go to the I/O ports. So we can have this kind of a configuration where we have two hard disks. We can read B3 and B4 in parallel. So in a sense, this will double our bandwidth. Of course, the flip side of this is that reliability, number one, is not there. And the second is that there is a high enough probability that we might want to read two odd blocks at the same time. So that will not be possible because for a given hard disk, we can only read one block at a time. So let us now consider a variation of this idea and let us call it RAID 1. So in RAID 1, what we do is that we take two disks. Well, we can take more than two, but let's consider an example with two. So let us assume that there are 5 blocks B1 to B5. So we simply replicate them across the disk. So we need to ensure that this copy of B1 is exactly the same as this copy of B1. This copy of B3 is exactly the same as this copy of B3 and so on. So the advantage of this scheme is that it is immune to one disk failure, which means that even if this disk completely fails, we will still be able to run the system in a normal fashion just by using disk number 2, right? Because there is complete mirroring between the disks. Furthermore, it is possible to read any pair of blocks in parallel. For example, we can read B1 and B2 or B1 and B3 in parallel from both the disks. So this, in a sense, doubles our bandwidth. So our bandwidth from the disks doubles. This is great, but mind you, all of this is being achieved with 100% extra overhead in storage. But yes, it is true that our total storage capacity, in a sense, is being divided by half with this strategy. But the advantage is we are doubling the bandwidth. Also, if one of the disk fails, our system will not perceive the problem at all. Then, of course, we can add one more disk, in the place, let's assume that disk 1 fails, we can add disk 3. So we need to then initialize disk 3 by copying all the contents of disk 2 to disk 3 such that both of them mirror each other. Now let's take a look at at an extension of this idea. So let us consider RAID 2, 3 and 4. So all three of them are actually in the same, belong to the same class, belong to the same family of RAID protocols. So here the idea is that we don't have 100% overhead in terms of storage. So 100% overhead was perceived to be a fairly large price that you pay for RAID 1. So instead what has happened is that in RAID 2, 3 and 4, what we do is that we create these disk groups. So let's consider we have 5 disks. So we have 4 disks for the data, disk 1, 2, 3 and 4. And we have one more disk called the parity disk. So what we do is that we divide data into small blocks. So a block in this case, in the case of RAID 2, 3 and 4, uh, does not necessarily mean that is 512 bytes. It can be smaller as well. So we consider one such, small block, one such chunk, and across the disk, so let's take B1, B2, B3, and B4. Across the disk, we perform an XOR operation, compute the parity, and set it equal to the value of the parity block on the parity disk. So this is exactly what is being computed over here. So we are computing the parity P1 as B1 XOR B2 XOR B3 XOR B4. So if you recall our previous discussion, then you would understand that if let's say any one of these disks fails, for example, let's say disk number 3 fails, then the information for B3 will get wiped out. But we can still reconstruct disk number 3 by basically computing B1 XOR B2 XOR B4 XORed with, exclusive OR with B1. So if we do this, we'll be able to recompute B3. So if there is a single disk failure, there is still no issue, there is no loss of data, because with the parity information, we can recover the data. And we can add a new disk in its place, which is of course starts out to be empty, and we can reconstruct its contents from the parity bits. So having a parity, we had seen that we had seen the notion of parity in the context of error correction and error detection. So this is something similar that if let's say one of the disk fails, so we are assuming a fail stop model of failure, which basically means that if a disk fails, it stops and the programmer is aware of it, the system is aware of it. So in this case, for example, what happens on one of my storage arrays is that if a disk fails, an orange button starts flashing. So this disk is removed. We put in a new disk and reconstruct the contents based on the contents of the rest of the disks and the parity. So note that if two disks fail simultaneously, then we will not be able to recover. So the block size in RAID 2, 3 and 4 is actually different. So in RAID 2, a block size is actually 1 bit. So we stripe data, bitwise across the disks. This is not really a good idea because, what we have also seen in chapter 3, from what we have seen in chapter 3, we don't access data at the level of bits. Sometimes, for some very obscure class of applications, we might be doing it. In general, we don't access data at the level of bits. So this will make it, makes access pretty complicated. Nevertheless, you can parallelly read out one stream of bits from here, one from here, one from here. So in principle, your bandwidth does increase. It's a somewhat better idea to actually stripe data at the level of bytes. But this is also not very practical. The reason is that if we, let's say, want to write something, we'll have to write to all the disks. So let's say we want to write in a 256 bytes, right? So a disadvantage of this scheme, RAID 3, is that since data is being striped at bytes, we'll write the first byte here, second byte here, third here, fourth here, fifth, sixth, seventh, eighth, and also compute the parities and write to the parity. There'll be a massive amount of traffic that is being sent to all the disks. So what is much more practical is actually RAID 4. And so RAID 2 and 3 are there in the spectrum, but they are not used. RAID 4 is used. So RAID 4, one advantage of RAID 4 is that we treat data as blocks of 512 bytes. So in this case, if we want to write 256 bytes, we can only write to the first disk, and then we can just recompute the parity. So recall that for recomputing the parity, it is not really necessary to read the contents of B2, B3, and B4. Okay, so this is a slightly profound result. So let me show a proof of this. So let us assume that we have four data blocks and we have B1 XOR B2 is equal to the parity. Now let's assume that we write to the first block B1 and we change its contents and we make it B1 dash. So now we want to find out what will be the new parity, and our claim is that we do not have to read B2, B3 and B4. So let us do a little bit of algebra. So let us compute B1 XOR so this, this the top implies that this is B1 XOR the parity P. Now what we do is any number exclusive OR, any block or any set of bits exclusive OR with itself is 0, and 0 exclusive OR with any other quantity is that quantity itself. So let's break this down. B1 exclusive OR B1 is again 0, exclusive OR B2 this is equal to, so this is a standard identity that 0 exclusive OR X is equal to X. So this is B2, all right, and which is sorry, this is B4, which is or the parity. Now let us compute the new parity. The new parity P dash is B1 dash exclusive OR with B2, B3 and B4, which we can write as exclusive OR. So recall that this quantity is equal to this B1 exclusive OR the parity P. So the new parity is basically given by this expression over here, and what this expression says that it is equal to the old contents of block B1 exclusive OR with the new contents of block B1 exclusive OR with the parity. So recall that there is absolutely no reason to read blocks B2, B3 and B4. This is a great advantage of the RAID 4 scheme, that to compute the new parity, especially when we are writing to a block, and we have also kept the block large enough such that most writes will only fit within the same block, so we don't have to access multiple disks. The problem with accessing multiple disks is that we essentially tie all of them up, and this restricts the bandwidth of the overall system. So for that, we have kept our block size large enough, 512 bytes. And to compute the new parity, it is not necessary to read the rest of the disks. We just read the old value of the parity on the parity disk, the new and old contents of the block that is being written to, and compute the new parity, which of course has to be written to the parity disk. So coming back to the slide, what we see is that RAID 4, which is practical in the sense it does not tie up many disks, has the same advantages as the rest of the RAID schemes in terms of computing the parity. And this is a direct corollary of Boolean algebra, that whenever a certain block is being written to, for example, if B7 is being written to, it is not necessary to read B5, B6, and B8. We only have to read the parity P2, and a new value of P2, which is P2 dash, is given as P2 exclusive ORed with the old contents of B7 exclusive ORed with the new contents of B7, which is something that we just proved. So in this manner, what will happen is that for any write, we will have to write to the given block. We have to first read a given block. We have to read the old parity, then update the block and the parity, right? So one write actually translates to two reads and two writes. So yes, there is some additional overhead in a RAID system, but the advantage is that if, let's say, any of these disks dies, for example, if disk 3 dies, we can still reconstruct it with the contents of the other disks and the parity disk. Furthermore, RAID 4 also has a bandwidth advantage. In the sense, it is possible to read multiple blocks in parallel. For example, we can read B10 and B12 in parallel. We can read, uh, B14 and B4 in parallel. So, of course, we cannot read two blocks resident on the same disk in parallel. For example, we can't read B18 and B10 in parallel. So, yes, there are some restrictions, but you know, it is expected that if we are getting a random stream of blocks, we'll be able to increase the bandwidth, the read bandwidth, by at least 4x, because they are expected to be to different disks. The requests are expected to go to different disks, and if they are busy all the time, all of them can be supplying data. So recall that when we are supplying data, it is not really necessary to read the contents of the rest of the blocks and the parity and compute that all of them are correct. I mean, even though it can be done, but this is typically not done in the interest of performance. Also, blocks themselves have error detecting codes. So if there is any problem in the block, we'll be able to find it. In addition, our failure model that we are assuming is a fail stop model, which means that disks have their own error detecting logic. And if they feel that there are errors which are not which cannot be recovered from, then and the entire disk is sort of in distress, then the entire disk fails. So in a typical RAID system, once a disk is in distress, we replace it and reconstruct the contents. So the take home point over here is that RAID 4 appears to be the better solution among RAIDs 2, 3 and 4, better in terms of mostly performance and bandwidth. But there are problems with RAID 4. The problem with RAID 4 is that every write we need to access this parity disk as well, one read and one write. So the parity disk might become a bottleneck, right? So if there are multiple writes to different disks, and since the parity disk is always accessed, it has a potential of becoming a bottleneck. Right? So for reading a single block, we have to access all the disks for yeah, so I'm just summarizing the performance aspects. So for 1 bit and 1 byte level striping, for reading any block, all the disks have to be accessed, which is a bad idea. That's the reason we went for RAID 4. But RAID 4 has a problem with this parity disk. Right? It's a single point of contention. So let us thus try to fix this problem with RAID 5. So in RAID 5, what we do is that we don't have a single parity disk. Rather, in a 5-disk system, we distribute the parity blocks across the disks. For example, for B1, B2, B3, and B4, we keep the parity block on disk number 5. Then for the next row of blocks, we keep it on disk 1, then on disk 2, then 3, then 4. So by rotating the parity blocks among the disks for for different rows of blocks, we were able to avoid that problem where essentially there was a single disk which was a point of contention. So we have distributed the parity blocks. So this again has the same advantages as RAID 4 without of course a single disk which becomes a point of contention. So it is reliable and has high bandwidth. So most commercial systems use some variant of RAID 5 because RAID 5 is fairly robust in terms of reliability, a fairly high performing solution. For example, we can in a 5 disk system, we can, unless two requests are to the same disk, our bandwidth will increase by 5 times because all 5 disks can be accessed in parallel. So if we need additional reliability, which means immunity to two disk failures, so recall that RAID 5 gives the immunity to only one disk failure. Say one disk fails, we can reconstruct the contents. But if we want immunity against two disk failures, what we can do is we can go for RAID 6, which gives you higher reliability and higher bandwidth, of course, but definitely higher reliability, and also the overheads for maintaining reliability are higher. So let us have two parity blocks where the parities are computed differently. So I cannot describe all the details, but if ever you take a course on field theory, you will get to know more about it. So what we do is that we have two disks and these parity blocks, I'm sorry, we have two blocks and these parity blocks are distributed across the disks uniformly. For example, for the first row, we have P1A and P1B on disks 5 and 6. Then for the second row, we have P2A and P2B again on disks 6 and 1. So in a similar manner, we distribute the blocks. So of course, since we have more parity information that is being saved, our effective storage capacity comes down. But the advantage is that even if let's say two of these disks fail, for example, let's say disk 3 and 4 they fail, we can always insert two new and empty disks in their place and reconstruct the data as well as the parity information from the rest of the 4 disks. So that is the advantage of RAID 6. But of course, in terms of performance as well as in terms of reliability, there are trade-offs. In the sense, it's more reliable, but it offers a reduced storage capacity because more bits go to store parity information. In the error detecting and error correcting information. And in addition, if let's say I change this block, then I need to read and write this block and definitely the other two parity blocks as well. So for any single write, there is much more traffic, and that reduces performance.